Hello everyone, and thank you to the Cosmology from Home organisers for the opportunity to give this talk. Today I'm going to present work I've done in collaboration with Jonathan Pober at Brown and Jonathan Sievers at McGill, in which we derive a general Bayesian framework for high-fidelity interferometric calibration, which is designed to solve the sky model incompleteness problem encountered when calibrating data at the precision required for 21cm cosmology. First, let's consider the signal of interest in 21cm cosmology. Hydrogen is the most common element in the universe, and when neutral hydrogen undergoes a spin flip transition from a high to low energy hyperfine state, it emits a photon at a wavelength of 21 centimeters and at a frequency of 1.4 gigahertz. As that 21 centimeter photon travels towards us, it's redshifted by the expansion of space, stretching its wavelength and reducing its frequency. As a result, the wavelength or frequency of the observed redshifted 21 centimeter signal maps directly to the time of emission and the distance from us of the hydrogen that emitted it. Additionally, the intensity of the 21 centimeter emission is a function of the ionization, density, and temperature state of the hydrogen along the line of sight. And as a result, the expected 21 centimeter signal fluctuates as a function of position. And correspondingly, the redshifted 21 centimeter signal is expected to fluctuate spectrally due to inhomogeneities in these fields along the line of sight. Due to the prevalence of neutral hydrogen in the universe, in the intergalactic medium at early times, and in galaxies at lower redshifts, the redshifted 21 centimeter signal is a powerful probe of astrophysics and cosmology between redshift 0 and about 150, when the spin temperature first decouples from the background radiation temperature. Highlighting some of the phenomena the signal can be used to probe, at early times during the cosmic dark ages before stars form, the 21 centimeter emission directly traces the underlying dark matter distribution and can be used to constrain the matter power spectrum. The linearity and simplicity of the signal prediction at this time means measurements during the dark ages are a sensitive probe of the presence of exotic physics or deviation from lambda CDM. Once the first luminous sources begin to form, the 21 centimeter signal is a sensitive probe of their impact on the intergalactic medium. And via their impact on the hydrogen thermal and ionization history, the 21 centimeter signal can be used to infer key properties of this period, such as the timing of primordial star formation, the luminosity and spectral energy density of the first X-ray sources, and the masses and star formation efficiency of the first galaxies. Additionally, at later times, once reionization completes, 21 centimeter intensity mapping of the residual neutral hydrogen in galaxies can be used to drive an independent measurement of the baryon acoustic oscillation power spectrum, and with it, the dark energy equation of state. However, being able to make any of these measurements hinges on being able to calibrate our experiments to an exquisite degree, requiring modeling of the shape of the instrument bandpass at a spectral fidelity better than 1 part in 10 to the 3. The origin of this high calibration fidelity requirement is the spectral means through which algorithms to detect the 21 centimeter signal aim to isolate it from the bright foreground emission. In order to observe the redshifted 21 centimeter emission, we have to look for emission from our own galaxy, as well as emission from a sea of extragalactic sources. That combined is 3 to 6 orders of magnitude brighter than a 21 centimeter signal of interest, depending on the frequency range, angular scale, and field observed. Fortunately, the redshifted 21 centimeter emission and foreground emission have distinct spectral structure. The redshifted 21 centimeter emission, which is shown on top of the foregrounds at 1,000 times its expected amplitude in red in this schematic picture, varies rapidly with frequency, which is in contrast to the smoothly varying synchrotron and free spectra of the foregrounds, shown in black. If the data was as shown in this picture, the 21 centimeter signal could be almost trivially extracted either by Fourier transforming the spectrum or jointly estimating a set of spectrally smooth and more rapidly fluctuating basis vectors. However, imperfect data calibration can introduce spurious spectral structure into the data, which results in foreground emission, shown in this blue curve, where again I've accentuated the level of spectral structure by a factor of 1,000 to make it visible. And where present, this additional structure will completely thwart unbiased recovery of the 21 centimeter signal by spectral means on the contaminated scales. And it is in order to prevent this contamination that extremely high fidelity calibration is necessary. Okay, so looking a bit more closely at the way one calibrates an interferometer and the means through which calibration systematics can enter the data, this slide shows a schematic of how interferometric calibration works. On the top row, you see the raw interferometric data signal chain, and on the bottom, the calibration forward model of the interferometric data. The standard way to calibrate a radio interferometer is by fitting the raw data with a calibration model comprised of a known sky model, a known instrument model, and a set of per antenna calibration parameters to be determined in the fit. The schematic I'm showing here is most directly applicable to sky-based calibration, but in practice, a similar step is also required for redundant calibration, so it's actually quite general. The difficulty with this calibration approach is that our knowledge of the low-frequency radio sky isn't sufficiently complete to derive calibration solutions at the desired accuracy with this approach. Errors and incompleteness in the calibration sky model due to uncertainties in low-frequency sky maps and flux density limited catalogs of extragalactic sources mean our simulated sky model does not match the true sky seen by the instrument, which means that even if we have an accurate instrument model, we will recover biased per antenna complex gain parameters in the calibration. And then when we apply that calibration, it will result in superior spectral structure in the calibrated data. And in a nutshell, this is the sky model incompleteness problem in interferometric calibration. Expressing that idea mathematically, we can write down a Gaussian likelihood for the gain terms of our antenna, little g, given the raw visibility data that we observe with the interferometer, VOBS. Here, Gm is a matrix which encodes the little g gain parameters. Vsim is a vector containing a simulation of the visibilities that we'd expect to get from the interferometer if the gains were unity, and n encodes the expected noise on the data. Then standard sky-based calibration simply involves finding the maximum likelihood set of little g gain parameters for this equation. Because the likelihood is a Gaussian, the equation is maximized when the exponent is 0. So if we can construct our simulated visibilities to be equal to the non-gain corrupted visibilities, V true, then the maximum likelihood parameters are an unbiased estimator of the true gain parameters of the instrument. However, the problem with this approach is that our simulated model is incomplete. Because of this, when we calculate the maximum likelihood solutions to the above equation, since Vsim isn't equal to V true, the maximum likelihood gain parameters are no longer an unbiased estimator of the true instrumental gain parameters, resulting in calibration systematics. Barry et al. And others have illustrated this effect in calibration simulations. The plot shown here from Barry et al. 2016 shows the two-dimensional power spectrum of simulated interferometric data, where the data is calibrated using the maximum likelihood fitted gains derived from an incomplete sky model on the left-hand side, and from a hypothetical perfect sky model in the center. Then on the right-hand side, the plot shows the difference between them. We see that calibration systematics have reduced the level of power in the bottom right of the plot in the so-called foreground wedge, and increased it in the top left, which is the corner of Fourier space referred to as the UR window, and is a region that in the absence of calibration errors, we would expect to be nominally free of foregrounds. So excess power here is particularly problematic because it can be misconstrued as a detection of the 21cm power spectrum, even using conservative foreground avoidance approaches to power spectral estimation. Okay, so I've covered the sky model incompleteness problem and its implications for 21cm cosmology. Now let's consider the possible solutions. These can be broadly split into 3 categories. Since the calibration bias originates in the difference between the brightness distribution on the sky and our model for it, the first and perhaps most direct approach is to gather more data to improve our understanding of the low frequency radio sky. The second is an instrumental solution, which is to build an instrument with an extremely spectrally smooth bandpass, because this enables one to restrict the spectral structure in the gain model when calibrating it in such a way that it's unable to absorb structure on spectral scales that would contaminate the power spectrum. The caveat to this approach is that if the instrument bandpass isn't spectrally smooth at a required level in reality, then hard restrictions on the spectral structure in the gain model can introduce calibration systematics by preventing true structure in the bandpass from being fit during calibration. Finally, the third and most flexible approach is to develop novel calibration algorithms designed to circumvent or eliminate the sky model incompleteness problem, enabling high spectral fidelity calibration without requiring the bandpass to be smooth at the level required for solution 2, and without needing more precise sky models than are currently available. And while in reality we want to progress with all 3 of these solutions, the third one is perhaps the optimal solution for analyzing data with current instruments and with our existing knowledge of the radio sky. The BayesCal framework is a solution in category 3 and directly addresses the sky model incompleteness problem in interferometric calibration while combining some of the best features of current approaches, including making use of array redundancy and imposing gain priors in parallel. The first 2 papers on this approach are currently in review, so keep an eye out for them on arXiv in the next few days, but I'll highlight a few of the main ideas from them here. Returning initially to the schematic for sky-based calibration I showed previously, and remembering that the fundamental problem here is that incompleteness and imperfections in our calibration sky model translate to biases in our fitted calibration gain solutions. BayesCal directly addresses this deficiency in standard calibration by supplementing the a priori known component of our calibration sky model with a statistical model for the emission that's missing in that a priori known component. Without any constraints on this statistical model, it would be degenerate with our calibration solutions, but we can eliminate that degeneracy by placing a power law prior on the spectral structure of the fitted calibration model, as well as a prior on the power in our statistical model derived from the completeness of the a priori known component, and performing a multi-frequency calibration. Additionally, we incorporate priors on the power spectrum of our gain amplitude solutions, informed by external constraints on the array from, for example, electric and electromagnetic co-simulation and reflectometry measurements of the receiver system. The benefit of doing this is that it enables us to make optimal use of our a priori knowledge of the instrument and sky, and by not approximating this knowledge using hard priors, it allows true structure in the bandpass to be fit for, even if it varies rapidly, if it provides a sufficiently improved model for the raw data, but downweights steady structure beyond that expected from measurements of the system in a probabilistically consistent manner. The combination of these features enables the calibration solutions to fit any true instrumental gain structure while disfavoring gain solutions with spurious spectral structure. This approach can be used to calibrate interferometers with an arbitrary antenna layout, but for calibration of interferometers with a redundant array layout, the computational efficiency of the algorithm can be greatly enhanced by using the fact that we have repeated measurements of the sky in the data to independently constrain the gain solutions. In this case, we can use BayesCal to fit for the subset of calibration parameters that cannot be fit for using array redundancy constraints alone, reducing the dimensionality of the Bayesian optimization problem we need to solve. The remaining parameters that must be solved for to calibrate the data are known as degenerate gains, and at each frequency they include the overall gain amplitude normalization for the array, called the degenerate gain amplitude, A, and two degenerate phase parameters, phi L and phi M, which correspond to tip-tilt phase shifts of the calibration model in the image domain. In the plots that I'll show next, it is these degenerate gain parameters, A, phi L, and phi M, as a function of frequency that we're solving for. In paper 2, we apply BayesCal to the calibration of simulated data on short baselines of the hydrogen epoch of reionization array. And the results of that analysis are shown here in purple. On the left for the ratio of the input and recovered degenerate gain amplitude calibration solutions, and on the right for the recovered degenerate tip-tilt phases. In both cases, the dashed black line shows the solutions one would recover with a hypothetical perfect calibration of the data. We also compare our results to calibration solutions for the same data set when calibrating either without any of the BayesCal enhancements or when only applying the BayesCal physical prior on the gains, with the results in these two cases shown in blue and cyan respectively. And additionally, we derive an equivalent set of calibration solutions using data from all baselines in the array, again with and without physical priors on the gains, which are shown in red and orange respectively. All the results I'm showing here are for a moderate incompleteness calibration model, which assumes a 50% uncertainty on the diffuse emission model and includes all point sources in the Gleam catalog with flux densities above 100 millijanskys at 150 megahertz in the calibrated field. We also repeated this analysis for high and low incompleteness sky models, and you can find those results in the paper. You can see in the left-hand plot, BayesCal has a negligible level of absolute bias in the recovered estimates of the degenerate gain amplitude, and significantly improves on the other calibration algorithms. In the right-hand plot, we expect the tip-tilt phases recovered using all baselines in the array, shown in red and orange, to be more accurate than those for the short baseline subset, shown in blue and cyan, for a fixed level of sky model incompleteness. However, by eliminating sky model incompleteness bias, we find that the degenerate tip-tilt phase solutions recovered with BayesCal are improved to the extent that they are competitive with those derived using approximately an order of magnitude higher resolution data from the full array when sky model incompleteness bias is not mitigated. In general, there are two types of calibration error that are relevant for 21cm cosmology: bias in the average value of the parameters, which is easy to see in this plot, and spurious spectral structure in the gain solutions, which couples the bright foregrounds into spectral modes occupied by the 21cm signal. To assess the spurious spectral structure introduced by errors in the degenerate gain amplitude solutions, we can calculate their power spectra. Those power spectra are shown here, and the color scheme is the same as in the previous slide, with BayesCal solutions shown in purple. The dashed line shows the noise-limited spurious gain amplitude power that would be recovered using a hypothetical perfect and complete calibration model. And we see that the BayesCal solutions approach this limit to within a factor of a few on all spectral scales in the data. The dotted line shows the level of spurious gain amplitude power in the degenerate gain amplitude solutions, above which foreground systematics exceed a fiducial 21cm signal model. And we find that of the calibration solutions tested, only BayesCal recovers solutions with sufficiently high spectral fidelity for recovery of the 21cm power spectrum in k-parallel modes below about 0.15 inverse megaparsecs. In addition to recovering high fidelity calibration solutions on all spectral scales available in the calibrated dataset, we expect a recovery at low k-parallel in particular to be important for 21cm cosmology in the medium to long term, as it facilitates attempts to push to 21cm power spectrum estimates at lower k-parallel values, including estimates within the foreground wedge, where the 21cm signal is expected to peak, and that are not feasible with calibration approaches that do not eliminate sky model incompleteness bias. The final feature of BayesCal that I'll highlight is that the calibration output is the full posterior probability distribution for the gain parameters. Isoprobability contours for the posteriors are plotted for the degenerate gain amplitude and typical phase solutions, here from left to right. A major benefit of this is that it enables calibration uncertainties to be covariantly propagated through to the visibilities and ultimately the 21cm signal estimates in a way that isn't possible when using point estimates like the maximum likelihood calibration solutions. And with that, I'll finish with these schematic plots showing the intrinsic spectral structure of the foregrounds and the signal on the left, the structure after standard calibration in the middle, and the structure after applying BayesCal, which allows us to recover a signal very close to the intrinsic emission on the right. And we expect this high spectral fidelity calibration with BayesCal to take us a step closer to the era of precision cosmology with the 21cm line. Thank you for listening, and I look forward to your questions.